Hello everyone, the title of my talk is Electromagnetic Characterization of Freshened and Offshore Aquifers on the formerly glaciated continental shelf of Prince Edward Island, and today I have the honor of sharing some preliminary results on behalf of a great team. This is the content of the talk. First, I will provide a brief introduction followed by some characteristics of Prince Edward Island through time and a bit of geology. Lately, I will show the work that has been done and the results I have so far. Even though the Earth is known as the blue planet, less than 1% of the water on the planet can sustain human life, and according to the United Nations, the demand of this resource has increased worldwide by about 1% every year since the 80s. Freshen and offshore aquifers, or FOAs, have emerged as a possible source of fresh water. However, what is a FOA? Well, it is water hosted in sediments and rocks below the seafloor with lower salinity than seawater. They were mostly formed during the last glacial maximum around 23,000 years ago, when lower sea level exposed continental shelves. Here in this figure, we can see some occurrences detected around the world. For example, FOAs hosted in lava tubes or volcanic units, as in Hawaii, pore space of poorly unconsolidated sediments, as in the east coast of the US, and fractured carbonate sequences around the island of Malta. The origin of this fresh water can be due to diagenesis, gas hydrates, meteoric recharge, or subglacial progressional injection. So why Prince Edward Island? PEI is located in Atlantic Canada, and Shaw and collaborators in 2005 and 2006 proposed a model for the Eastern Atlantic margin evolution. Here in this figure, PEI is inside this square red box. We can see that during the last glacial maximum, PEI was completely covered by the Laurentide ice sheet, around 23,000 years ago. The dashed blue lines show ice division, and the thin blue lines are general ice flow lines. In the following plots, we can see the ice retreat and the maximum extension of PEI when the low sea level maximized land exposure. This allowed meteoric and progression emplacement. This happened around 9,000 years ago, and the last plot shows the Iceland's current state. In PEI, we can find mostly late Devonian to early Permian sedimentary rocks. Onshore aquifers in PEI are located in highly fractured red beds, including the Peak 2 and PEI groups, but in particular in the Naufrage Formation. This is a conceptual model proposed by Paradis and collaborators in 2006, where they describe a series of red bed layers hosting the aquifers intervened by mudstone layers. Also, some superficial sediments are present on the island. Offshore wells identify the presence of the Naufrage Formation in the Gulf of St. Lawrence. Therefore, it is possible to think that offshore fractured consolidated sandstone host offshore aquifers. To test this idea, in 2021, we acquired geophysical and geological data offshore PEI in the Gulf of St. Lawrence. Among all the data collected, my project is based on the marine electromagnetic data. In total, we acquired 85 kilometers of EM data in the Gulf, as you can see in this figure, and here you can see a zoom of one of the profiles on the north of PEI. The yellow line shows the transmitter's path, and the 12 purple dots represent the ocean bottom electromagnetic receivers, or OBMs. OBMs are instruments that measure the two horizontal components of the electric field and three components of the magnetic field, figures 1 and 2. In figure 3, we can see the KGM system, which is the transmitter we use to create artificial electromagnetic fields. It consisted of two 9-meter orthogonal dipoles, one in this direction and the second one perpendicular. Here I am showing an example of the data acquired, and since we use two dipoles, P1 and P2, and we measure two horizontal components of the electric field, E1 and E2, we have 4 transients per TX transmission. The plot shows the transient after stacking, blue lines, and the standard deviation with the red shaded area. Once all the transients were processed, I performed 1D inversions. After inversions and applying a 2D interpolation, I got this pseudo 2D model. The black dots on the profile show the position of the 1D model after the inversion. We can also see the OBMs on an echo sounder profile acquired along the EM profile. Just please notice the vertical scale of 3 milliseconds, and the map in the center shows the location of this profile. Along the pseudo-TD, we can identify an almost continuous resistive layer with 13 to 16 nm around 50 to 100 meter depth below the seafloor. The arrows show the position of two gravity cores acquired along the EM profile, GC06 in red and GC7 in navy. These scores show low salinity values around 26 practical salinity units. In conclusion, the presence of offshore freshwater seems feasible based on the geological context, and also the preliminary results suggest the presence of resistive anomalies, and these anomalies match with the gravity cores with low salinity values. Finally, I would like to express my gratitude to the Geological Society of America for the Graduate Student Research Grant awarded in 2022, and to Anja Shah for the opportunity to present my research here. Thanks for your attention.